So we can start the first session of the afternoon, and the first speaker is Gili Bisker from Tel Aviv University, and she also will talk about estimating inferring entropy production.
Thank you very much, Juan, for the introduction. Thank you very much for the organizers for this lovely meeting and for the opportunity to present my work. So I'm Gili, I'm from Tel Aviv University. I will talk about formalizing an optimization problem for inferring the entropy production from observed statistics. By the way, I know some of you have visited, but if not, I encourage you. This is our campus at Tel Aviv, and this is the beach line at Tel Aviv. Okay, so when we think about small systems or molecular systems, of course, they are subject to thermal fluctuations, and they're therefore stochastic. And here you see a cartoon of a molecular motor carrying a cargo and walking along a filament, a subcellular filament. And this motor uses some chemical fuel, such as ATP. And by hydrolyzing it and exploiting the free energy, it can do work. But some of the free energy is dissipated. So we have irreversible heat dissipation that is casted as an increase of the entropy of the environment. So in essence, the entropy production constrains the amount of extractable work, giving some energetic budget. So we care about entropy production. However, of course, this is on the left, it's obviously a cartoon we can never measure with such of a great detail. And what we can measure in practice is perhaps the position of the molecular motor and not, let's say, its internal configuration. So like we've just heard, the entropy production rate can be estimated by the distinguishability between forward and reverse trajectories, quantified by the Kullback-Leibler divergence, and you can see the formula here on the right that Juan presented. And we have a lower bound on the total entropy production rate because we don't have all the information or all the statistics about the trajectory, all the data about the trajectory. And the relative entropy, or the Kullback-Leibler divergence, which measures this distinguishability between forward and reverse, is given by the following formula. And it basically tells us how different two probability distributions are. Okay, so to set the stage, I work in the framework of stochastic thermodynamics. I envision my system to be represented as a graph, where each node represents a microstate, and each edge represents a transition. And then if I follow the trajectory over time, I see the system in terms of like which state it is in as a function of t, time. And so this is a continuous time Markov chain process. The physics is within the rate matrix that describes the rates of the transitions between each of the states. And the dynamics evolves according to a master equation. And if you write it down, the change in time of the probability of being at state I is just the sum of the ingoing flux minus the outgoing flux. At the long time limit, the system reaches a steady state, which I label with pi. So this is the steady state probability distribution of observing the system at one particular state. And then you can write the steady state entropy production rate in the following way. So you have a sum over all the edges, and there is a multiplication of two terms. One of them is the current over the edge, over the link, times the thermodynamic force, which is given by this formula. And of course, this quantity is always greater or equal to 0. So it's convenient to also introduce this notation, the mass rates. So Nij is the mass transition rate from state I to state J, which is just a multiplication of the steady state probability times the transition rate. And if I have full information on the trajectory, I can restore, of course, the rate matrix, because, for example, if I measure the total time that I see the system at state 2, divided by the total time of the trajectory, then I get the steady state probability distribution. And if I count the number of transitions between state 2 to state 3, divided by the total time, I get the mass transition rate. Okay, so I can also write the entropy production rate using the mass rates, so this is a more compact form. And the issue that we're dealing with, or we're interested in, is the issue of partial information. So this is a very simplified example. So imagine that I cannot resolve between state 3 and 4, and I can only see a single lumped state, coarse-grained state, that I label H for hidden. And this is the only information that I can have about the system. So given partial information, as we've heard before, we get a lower bound on the total entropy production rate because we cannot restore all the information about the trajectory. And the observed dynamics are no longer Markovian. And in this particular case, we get a second-order semi-Markov process. Okay, so we have the general issue of general framework of coarse graining. So I can have many microstates, and they can be lumped into larger macrostates or coarse grain. So instead of seeing the detailed trajectories, this is what I can observe. I can observe the coarse grain states, and only, for example, the coarse grain state I, J, and K, and the transitions between them. So of course, this is non-Markovian dynamics, and the question is, how do we estimate the entropy production rate from the observed trajectory? Okay, so I will start by describing several bounds on the total entropy production rate, and then I will introduce the new bound that we have suggested. So this is the passive partial entropy production rate. It was proposed by Shirashi and Sagawa in 2015. So we have the system that I've described before. I have 4 states. I cannot resolve 3 and 4, so I only see H. So I only see the 2 observed microstates are 1 and 2, and of course the transitions between them. So here I calculate the entropy production rate from the transitions between the observed Markovian states. So instead of, so this is the formula, so instead of summing over all the links, I only take the term that corresponds to the 1 and 2 link, which is between the 2 observed Markovian states. So this is just one term out of the sum. And again, in the notation of the mass rates, again, this is the current over 1 to 2 times the affinity over this link. And this link, this term vanishes if I don't have any currents. Okay, so if I cannot measure a current between 1 and 2, I will get the trivial bound of 0. The next one is what we've just heard. This is the Kullback-Leibler divergence bound. So this is work with Juan and Iñaki and Jordan. So we have a very similar setting. And here, as I mentioned, the dynamics that we get is of a second-order semi-Markov process. So instead of considering the states, we considered 2 consecutive states that we label, for example, I and J, where J is the current state and I is the previous state. So we sort of like cast the observed dynamics from a second-order semi-Markov process to a first-order semi-Markov process. And this is the formula that we have seen. We have applied the Kullback-Leibler divergence to these sort of trajectories, and the calculation for the relative entropy between forward and reverse trajectories give rise to 2 terms, 2 contributions. One is coming from the affinity, and the other one is coming from the waiting time distributions. So the affinity basically measures the affinity of the observed cycle, for example, 1, 2, and H in this case. And this term vanishes when there's no current. And the other contribution comes from the waiting time distribution. So here, for example, I compare the waiting time of the system at state age, given that I entered to age from 1 and I exited to state 2, and the reverse. What is the waiting time that I spent at age, given that I came from 2 and I exited to 1? And here you can see an example of a calculation and immediately see that these two waiting time distributions are not identical, which is an indication of time irreversibility. And by calculating the Kullback-Leibler divergence between such waiting time distributions, you can get the contribution for the lower bound on the total entropy production rate. And this can be, of course, different than 0, even if we don't have any currents in the system. Another bound is the sigma 2 bound. This was proposed by Skinner and Dunkel in 2021. So they considered a similar system. And here they took the first and second order transition statistics. So the first order is just the mass rate, and the second order is the second order mass rates that I labeled here as Nijk. So for example, if I see this observed trajectory, the first 3 states that I see 1 and 2 and H, so this is considered 1 to H. So this is like a second order observable. And then they transform the system into a canonical form, and this canonical form conserves the considered statistics while not raising the entropy production rate. Okay, so this is the procedure that they introduced in their paper. So let's say they have a system with many internal states that are coarse-grained. So for each state, for example, in this macrostate J, they redirect the mass rates such that they diminish the internal connection within the coarse-grained state, such that, and they do it microstate after microstate, and they reach to this situation where all the internal states within the macrostate J, they don't link between each other. Okay, so the only links that they can have is with external states. Okay, so they have this construction. Again, this construction, they proved that it can only lower the entropy production, and it preserved the statistics that they chose to focus on. And then they formalize an optimization problem using the observed statistics of the first and second order mass transition rates. So they basically minimize over all the canonical systems that have the same observed statistics. And then they take the minimal value of the entropy production, which trivially gives a lower bound on the total entropy production on the system in question, because obviously the system in question is part of the group over which we minimize. Okay, and then they just like count over all the states and correct for the double counting. Okay, so this is the sigma 2 bound. So just as an intermediate summary, just to highlight which information is being used for each of the bounds. So for the passive partial entropy production rate, we only took the transitions between the observed Markovian state. For the affinity, we took the statistics for second order semi-Markov process, so only transitions. For the KLD bound, we took the statistics for the second order semi-Markov process, both the transitions and the waiting time. And for the sigma 2 bound, we took the first and second order transition statistics of the observed state. So how do these relate? So we have some hierarchy. So the passive partial entropy production is always smaller than the affinity. This was proving in this 2017 paper, which is always smaller than a KLD because it is one contribution, right? Because the KLD is also with the waiting time distribution. And then Skinner-Dunkel showed that the sigma 2 bound is larger than the passive partial entropy production. So you might wonder why they're not on the same line somewhere. Well, you cannot put them on the same line, and this is what they say. So in their paper, they shown several examples, and in all the examples they showed, the sigma 2 bound was better than the KLD bound. However, it's not always the case. And what they say So we say it's possible to construct systems where just the waiting time distribution contribution is larger than the sigma 2. So what they suggested is one could define an estimator, which is the maximum of the sigma 2, and the sigma 1 plus sigma waiting time. So sigma 1 plus sigma waiting time distribution in their notation is just the KLD bound, to construct what is currently the best possible estimate. Okay, so I cannot put sigma 2 in the same line as the affinity and the KLD. Okay, so what did we do? So this is our proposal, and I want to highlight Eden, who is the graduate student who has been working on this project. So we consider the following. We consider the steady state probabilities. We consider the first and second order transition statistics, so the mass rates in IJ and NIJK. And we also consider the conditional waiting time statistics that I label with psi, IJK. And I require knowledge about the underlying topology. Okay, and I will go back to that soon. And we suggest the following bound, okay? So if I know the underlying topology, okay, so let's say this is the system that I observe, and I have some knowledge that this is, in fact, the underlying system, then I'm going to search over all the systems according to the topology, such that the observed statistics match the statistics of the system.
So, Gili,
yes.
By topology, you mean the number of states and the connections?
Yes, the number of states and the connectivity, precisely. Okay, so I look over all the systems that look like this, such that the observed first order transition rate, second order transition rate, steady state probability distribution are equal, and also the same waiting time distribution. So this is a lot to ask, okay? And of course, this gives me a lower bound on the total entropy production. And I called it sigma optimal infinity. Okay, so we can have analytical expression for all the observables. So all the observables can be written down as functions of the steady state probability distribution and the mass rates. So, so these are the variables for the optimization problem. And of course, we have some constraints. So these are the linear constraint. The first one is just probability conservation. Of course, I want the probability to be in the macro state to be the sum of the probability of being in the microstates. And we have mass rate conservation. Okay, so I want the coarse grain mass rate to be equal to the sum of all the rates going from state I to state J. And I also require mass conservation at each state I being at a steady state. And of course, I have nonlinear constraint. So the second order mass rates and the conditional waiting time distribution can also be expressed in terms of these variables, but you can find the formulas in the paper. I didn't put them here. Okay, so this is what we wanted to do, but requiring an equality between two continuous functions as part of an optimization problem is really difficult and not very practical. So instead of requiring the full probability distribution of the waiting time, we chose the moments of the waiting time distribution. So we call it sigma optimal n. And here we require equality up to the nth moment of the waiting time distribution. So now we can compare numbers and not functions. This is easier. And then we can have a hierarchy of lower bounds given the number of constraints from the moment of the full distribution. Okay. And of course, we can get also the values of the moments from derivatives of the Laplace transform of the conditional waiting time distributions. Okay, so to complete the picture for our bound, which we call sigma optimal, we require the steady state probabilities, the first and second order transition statistics, the waiting time statistics, or the moments of the waiting time statistics of the waiting time distribution, and their underlying topology. And now, and this is what we show in this paper. Now we have a better bound that outperforms previous ones. Okay, so results. So this is the four-state system that we have considered, and these are the results. So I'm plotting the entropy production rate versus some force F that I apply on the observed link between the states 1 and 2. So the black one is the total entropy production rate. And what you see here in this red axis is the result of our bound. And here, I only use the first moment of the waiting time distribution. So this was enough to give me a very tight bound. And you can see that it's much better than, for example, the KLD, which is in blue, the affinity, sigma 2, and the passive partial entropy production. So in this case, all these three, the passive, the sigma 2, and the affinity vanishes at stalling conditions. By the way, they seem very similar, but the affinity here suppresses sigma 2. Okay, and another example of a molecular model. So you heard this model before from Juan. So we have a molecular model walking along a one-dimensional line, and in each state, it can have two internal conformation. One is passive, one is active. From the active, it can hydrolyze ATP, so we have this chemical potential, and this motor operates against a force. What I can measure is only the position, so I cannot resolve internal states. And also here, so these branches are for different values of the chemical potential, of the activity in the system. And I'm plotting the entropy production rate versus the force. So the black line is the total entropy production rate, and what we get for our bound. Again, also, just by considering the first moment of the waiting time distribution, okay, so you can see I get a very, very tight bound. Okay, so what happens if we don't know the underlying topology, because this is a very strong assumption? So we assume a simple model, okay? So we tested, so let's say these were the real systems, okay? So I can have perhaps 2 internal states, 3 internal states, or 4 internal states that are coarse-grained to one hidden state. But I only assume a simple topology where I only have 2 states in the coarse-grained state. So I still get a lower bound on the total entropy production. So if I don't know anything, I can just make a guess and still get a lower bound. So here you can see results for both the 4-state system and the molecular motor system, and I'm plotting the result of our bound, the sigma opt 1, versus the total entropy production, and you can see that it is always a lower bound, and I'm plotting different markers for 2 states, 3 states, and 4 states. Okay, I will skip that. Okay, so I do want to advertise my group. So in addition to thinking about quantitative measures of non-equilibrium inferred from partial information, we also think about non-equilibrium self-assembly from theoretical perspectives. And I'm also an experimentalist, and I'm using near-infrared fluorescent single-wall carbon nanotubes for imaging and sensing. So you can see here single-wall carbon nanotubes floating around in solution, visualized by near-infrared fluorescence microscopy. We can monitor from the fluorescent signal self-assembly around the nanotube. We can monitor enzymatic activity. So here you see nanotubes lighting up, indicating that an enzyme cuts a molecule. We do imaging in the near-infrared, including in active and live systems. So here you can see the contraction of the GI tract of a C. elegans nematode worm. And we also sense biomolecules with single-wall carbon nanotubes. Okay. So to summarize, I have shown you a new bound on the total entropy production rate. And I've compared it to other bounds in terms of what information is being used to construct each of the bounds. I have shown you the hierarchy of the bounds, and I show you a result for the 4-state system, the molecular motor. And just as a perspective, it would be very interesting to put this in a larger perspective and compare it to other bounds that were suggested. So for example, there are bounds that consider transition-based statistics instead of states. So these works were suggested by Udo Seifert's group and Edgar Roldan's group. There's also snippets statistics that combined observed states and observed transitions. There's also the TUR, of course. And there is another bound that we have proposed. We call it reformulation of the semi-coarse grain data, which uses a different information. So I'm still thinking how to compare apples to apples because it's not that trivial. But anyway, it would be very interesting somehow to have a very wide perspective of lower bounds on the total NP production. Okay, so thank you very much for your attention. That's it. Thanks.
Great, thank you, Gili. So questions, for questions, first students.
Hi, thanks for the talk. I had maybe it's a silly question, but how do you decide what states to coarse grain? Like in the 4-state model, only 3 and 4 states were coarse grain. What if we coarse grain 1 and 4?
Okay. Yeah, it's a great question. So it depends on the system. So this is just a generic model that I just showed 2 states, but the procedure would be completely identical regardless of the states that I chose to coarse grain.
Gili, I mean, from an operational point of view, of course, requiring knowledge of the underlying topology is a lot to ask. So I like particularly this last case. But I mean, the simplest picture now seems to be to just assume the simplest topology for the hidden stuff, right? Do you have any idea how that improves if you include more states? That's question number 1. Number 2 is I will show tomorrow the improvement concerning the whole waiting time distribution. So within your approach, I mean, including the second moment of the waiting time distributions would yield much better result or only in epsilon better? Can you comment on this?
Yes, thank you very much for the questions. So 2 things. What did I want to say? Yeah, okay, so here. So what we tried is, let's say that I don't know what is the topology, and I assume a simple topology. So I do get a lower bound, but how does it compare to other bounds? So here we compared, so let's say we had 3 states, but I assumed 2 states. So still our bound, which is here in the red axis, was better than the bound you could have gotten from the KLD or sigma 2 calculations. So this is one thing. And regarding the other question, so we tried also with the second moment, but we didn't see much of an improvement. So most of the information in these cases was contained in the first moment of the waiting time distribution. So because it didn't show much of an improvement, we just stay there. Perhaps, I mean, of course, I can imagine other scenarios where, of course, higher moments would contribute, and then you can then choose where to stop the calculation depending on how much statistics you have and how much computational power you have. But it's completely generic, and you can always go, I mean, given you have all the resources, you can, of course, go higher and higher until you say, okay, I don't get any more information out of the statistics.
Related with this question, it could happen that if the topology is not the correct one, let's say, and if you include a lot of moments, there is no any solution. I mean, there is no any possibility of fulfill the constraints. This could happen.
So again, if I don't have the topology and I guess something that is wrong, you mean?
Yeah. So yeah, you take the simple one and the simplest one, and the topology is much more complex, and maybe it's impossible to satisfy the constraints.
Interesting. So in the systems that we have checked, it didn't happen. But yeah, perhaps there could be some, a pathological example that when you assume a simple model, you cannot satisfy all the constraints. And then, yeah, we haven't ran into such a situation, but I don't know if this situation does not exist.
Hi, thanks for the very interesting talk. So this last slide you just showed.
This one.
Yeah, so is this right that with higher observed states, the bound becomes looser?
I cannot make this claim. I don't know if this is just because of the choice of the parameters. So I don't think this is a general thing. I think it's just incidental.
Okay, thanks.
I have one more question.
Yep.
And that, well, the results are impressive, no? I'm wondering if this is because the motors or the networks are very optimal, because, well, you are optimizing the entropy production. Is because they are very optimal, or because the range, if you calculate the maximum entropy production, is very tiny, the range?
So I'm not sure. Yeah, so I think I have, yeah, so here, for example, you see, so here we checked what happens. So like when you do an optimization problem, there is a hyperparameter that you need to define, which is the tolerance, the constraint tolerance of the optimization. So here you can see how good the bound is. So this is, I'm plotting the entropy production rate versus the constraint tolerance. This is for the four-state system. This is for the molecular motor. So this is the real entropy production. And the red one is what we get from our bound. And of course, as we have smaller tolerance, we get closer and closer to the bound, but you see that eventually it saturates. So here, there is some difference. Previously it was presented in a log scale, so it vanishes, right? In the molecular motor case, indeed, it's very close. I'm not sure what is the feature of the system that helps you predict it so tightly just with the first moment of the waiting time distribution. This is something that we were trying to understand, but we're not sure we understand it completely. But it's an interesting observation, I agree.
Because your approach is also a good benchmark for motors to see if they are close to the optimal or not.
Yeah, indeed.
Okay, any further question, Bella?
Thank you, very nice talk. Regarding these bones, when do they reduce to equalities? There is, for example, when this sigma KLD will be equal to sigma 2.
So you're asking about.
Yeah.
So here, when sigma 2 equals the sigma KLD.
Yeah.
So this is very, very interesting. So after we saw the paper by Skinner and Dunkel, we were sure that the sigma 2 was better than the KLD because in older examples, it was better. But when we started calculating, we found that you cannot even compare between sigma 2 to the affinity. So for example, in the examples that I've showed, sometimes the sigma 2 was smaller than the affinity. And this is, again, something that it is related to the previous question. So this is like trying to understand what are the important features of a system that, affects like how well each of the bounds are. I don't have a general answer, so I'm sorry.
Okay, because I'm trying actually opposite to understand what are the important features of KL divergence that set up this bond. If we change KL divergence measures, this is actually, it was the question. And then I'm wondering if, for example, if we consider first bond, we have two inequalities. When the first inequality reduces to equality and when the second inequality reduces to equality.
Okay, so first, the information that you use for each of the bounds is different. So starting from this point, it's intuitive that as you use more information, it's reasonable to assume that you will get a tighter bound. For example, these two become an equality when you don't have contribution from irreversibility in waiting times. So if in some cases, when you coarse grain and you don't, yeah, so this is one example, for example, that Juan gave. So if for example, you have a molecular mortar and you only have internal states such that transition between positions only happen from the same particular microstates, then after you coarse grain, you will not get a contribution from irreversibility in waiting time contribution. So it depends on the, let's say, of the particular topology of the system and the way that you coarse grain. So if you don't have contribution from irreversibility in waiting time distributions, then all you can get is the affinity, and then the KLD will equal the affinity in this case.
Okay, thank you very much.
Okay. So, further questions? Yeah. Zahar.
Hi, thank you for the nice talk. Have you checked if like the bound that you get with topologies that is the good one, because you know what, right, is the best one? So can you guess the topology in some manner, right?
Yeah.
Okay.
Sorry, I didn't understand the question.
Okay, so let's say that you have 4 states and you hide 2, and so
Yeah,
you have.
okay.
Have you checked if by like pretending that there is 5 states and calculating, so can you guess the topology by having the higher, the best bound?
So we haven't, yeah, it's an interesting question. We haven't tried it. We always like say that, if you don't have any information, just guess the simplest case, and then it's good. But it is something that would be very interesting to check. I mean, maybe I would assume that even if you guess wrong, I still think you will get a lower bound because of the constraint of the observed statistics is pretty, is significant. But we haven't tried it.
Okay. If there are not further questions, let's thank Gili again.
Thank you.
And our next speaker is Christoph